Hello, John Golden, here again from the Calculus Cave. They do let me out occasionally. It's been nice weather lately. So today is a video to go with day 4 of our calculus class, and it's about this idea of the Riemann sum. Now it's a little weird to hear Riemann's name attached to this, but he came along a fair amount of time after Newton and Leibniz. So the idea is really from Newton and Leibniz, but it was made precise later by Bernhard Riemann. So we call them Riemann sums after his kind of precise formulation of the ideas that we're talking about now. So Newton did this kind of by himself, working on these physics problems, building on the work of the mathematicians before him. But then he didn't share the method. He called it fluence. So once he had a relationship, he talked about what's the fluent of that quantity. And by what he meant by that was kind of the accumulation. So Leibniz, when he developed his, he shared his work with other people. So a lot of our notation comes from Leibniz as opposed to coming from Newton. Okay, so we were dealing with before this idea that we could approximate. We could kind of measure accumulation by adding up these step graphs, where the kind of quantity being added, we're imagining this is some number being added each time. And there was a connection to thinking about that in a continuous case. What if it was kind of a constant stream instead of 3 coming in, then 4 coming in, then 5 coming in, by thinking about it as the area under this curve. So Leibniz realized that connection also, and people have been thinking about trying to find areas of curved objects before. So like, for example, the area of the circle, that's a famous one. That was proven by Archimedes 2,000 years ago. So these curved objects are difficult, and then that becomes the general problem that Leibniz is trying to solve. So how he thinks of it is, what if I could approximate better and better and better? And he wants to imagine the perfect approximation. So instead of 10 rectangles, 11, 12, 13, 14. And notice what's happening to the area up at the top. Right? So we've got this, the digits are kind of eventually locking down. So what do you think? Is it going to stay 65 hundredths? No, 66. The changes are getting smaller and smaller. We're going to get up to 67 hundredths? Yes. Oh, but it took a lot of rectangles to get up that far. So what Leibniz realized as he's working on this is that these approximations, we could kind of imagine them getting more and more accurate. And how he did that was he imagined that original width of the rectangles is taking a smaller and smaller width. Now, it's a little weird because if we think about it kind of going all the way, then the rectangle has 0 width, which means it has 0 area, we would think. But then the number of rectangles is also increasing. So it's true we've got smaller and smaller bits of area, but we have more and more of them. So if you even look at our diagram, by the time we get up to 100, this graph just goes from 1/2 to 3. So that's 2.5. 2.5 divided by 100, right? That's 25 thousandths. So that's a tiny width for the rectangle. Yeah, but because we have 100 of them, they still add up to this number that's roughly equivalent to what we had before, ever more accurate. So Leibniz realizes that even though he's imagining the width of the rectangle is going to 0, somehow it balances out with the number of rectangles. And this is a problem that really goes back to the ancient Greek philosophers who were trying to think about infinity for the first time. for the first time that we have recorded. Now, so he develops this technique to then imagine what's kind of the logical conclusion. Okay, so we're going to imagine we have an infinite number of rectangles, and he comes up with this notation for it. He liked thinking about it like with the Greek sigma for the sum, so he draws a long stretched out S to represent that he's still summing. And he used this notation to represent what he's summing up. So this expression here is giving the area of these impossibly thin rectangles. The function is the 3 plus a half x. And so that's giving the height of the rectangle. And he's imagining this dx, the differential, to be the width of an infinitely thin rectangle. Okay, so now after he's and Newton have developed the calculus, that this is where people attack it. They say that this part here is nonsense. We just can't, you can't have an infinitely thin rectangle that somehow adds up and has area. And their argument was, well, but look, it works, right? So if it works, who are we to argue with it? And it wasn't until later when mathematicians started to iron this stuff out. And we'll talk about those people later in the course. But for now, this idea is that we're going to pass from kind of the rough imagination to this perfect approximation. And so the next part of the video, I'll just be playing around with a couple different curves and seeing what we can notice. Okay, so first, before we move on, let's just check and make sure that this is correct, right? So if the actual area under f of x is this number, or at least this approximation of the number, maybe we should move to a different limit here. Okay, so now it's saying 11 and a quarter. That's probably an exact value. And let's see, right? So we've got the 9 squares of area, and then we've got this bit here. So this is a triangle, 1.5 tall, 3 wide. So 3 times 1.5, that's 4.5. 2 and a quarter, right? Because half base times height. So 2 and a quarter plus the 9 squares, 11.25. So this integration technique, that works. At least on this example, right? You should never believe anything with just one example. Let's change the function and see how it works a little bit. So let's see, we could do 1 plus x squared. Okay, so now this is, we can start to see some value maybe, because if I asked you to find the area for this bit, that'd be difficult, right? So the approximation idea makes a lot of sense here. Right, so that would be one way to do it. So this estimate must be an underestimate because we can kind of see all the gaps under the curve. People have played around, Riemann in particular thought about this, playing around with kind of, well, where do we sample the function for the height of the rectangle? So we could take it in the middle. Now this looks like it's probably pretty accurate, right? Because sometimes it's a little bit under, sometimes it's a little bit over. I bet you those come pretty close to balancing out. And then this would be for sure an overestimate. So let's see how close we got here. With 10 rectangles, we got 4 66/100ths. The actual, well, it looks like it might be 4 2/3 or close to that. So that's pretty close if we got to within 100th with only 10 rectangles. That's nice. All right. What about if we take something even funkier? Okay. So this, let's see, if we were estimating it, it looks like we've got almost 1 and almost a half. So this number of about 1.5, that makes sense. The actual is this, and we can see the estimation again. Pretty close. That looks like it might be within 2 thousandths. astounding with only 10 rectangles. So after they've come up with this method, they realize pretty quickly that, oh, that's interesting. All right. Do you ever wonder how much area was under just one kind of chunk of the sine curve? It says it's 2. That seems a little hard to believe, doesn't it? How could it be 2? All right. So once they've come up with this technique, now they're wondering about all sorts of things. They have a technique that can find the area of objects they've never been able to find before. And math also often follows this pattern, right? It's like we've got this idea, we worked out something new with it. Oh, what's next? What can we apply it to? How can we use this tool? Right? So this idea of the integral, which is the term that Leibniz used for it, um, instead of fluent, like Newton called them. But this idea of the integral is so powerful. It solves this whole new class of problems that people have only been able to approximate before, and it gives exact solutions. So in tomorrow's lesson, what we'll be looking at is some ways that we can apply this idea of the integral. Okay? If you have questions, comments, things that would make this clearer or better, please post to Piazza, or the lesson pages always have comments turned on. You can post there. And thanks very much. We'll talk later. Bye-bye.